So I'd like to again thank the organizers for bringing us together to talk about these really exciting opportunities for collaboration on a really important problem. My name is Anand Gnaadadesikan, and I'm leading the first panel with Dr. Raghavan Krishnan, I'm a climate scientist. Dr. Krishnan is the director of the Indian Institute for Tropical Meteorology, which is a global player in the climate sphere. I will share my screen. And so I wanted to actually start by setting the groundwork here with some key questions. I realize that many of the folks on this call, particularly those who've been participating in the Gupta-Klinsky Institute for years, are coming more from a health sphere and less from a climate sphere. So I thought it would be helpful just to start off by talking a little bit about what we mean when we talk about climate change, to talk a little bit about what we can say and not say about how climate change works and how it might affect India, to lay out some of the opportunities for collaboration between Hopkins and Indian institutions and via Hopkins through other institutions in our area. And Dahlia has made an amazing case for the kinds of resources that are in our area here. So just to remind people what climate change is, there's a statement that we often make that climate is what you expect and weather is what you get. And what this means then is climate change is then any change in the statistical distribution, the mean or the variance or some extreme probability of some aspect of the climate system, which can be temperature or rainfall or radiation. All of those things may have specific impacts on specific parts of society. Climate change can be anthropogenic or natural. We often talk about the anthropogenic climate change, but it may often be the case that preparing for natural climate variability actually increases our resilience to anthropogenic climate change. This is, of course, however, not universal. For example, if anthropogenic climate change is causing increases in hurricanes, then being able to predict hurricanes and deal with coastal protection benefits not only us when natural climate change enhances hurricane activity in a particular season, but if anthropogenic climate change is causing glaciers to melt and reducing water supplies, that is not something that we can necessarily deal with in the same way that we deal with natural climate change. The timescales that we deal with here start on a few weeks and can go up to geological timescales. And in this session, we're going to be most interested in the next century. So something that I think is important to remind people is that why is it that we can predict climate beyond a few weeks? It's not necessarily obvious to the public, not necessarily obvious to some of the skeptics whom which we'll be talking. And a point I make to my students when I teach Introductory Global Environmental Change is that we all make climate predictions every year, right? We make climate predictions when we travel to another part of the world and we change the clothing that we use. We make climate predictions when we say, I'm going to take my winter coat out in the wintertime, or I need to make sure I have a good umbrella as the monsoon is coming. The reason that we can make those predictions is that there are large scale and long-term gradients in temperature, rainfall, and across the planet. And these are really controlled by energetic balance, how much energy is coming in and how it's redistributed. Weather involves changes in where these gradients between, say, warm and cold or moist and dry air are found. And locally, it can involve large changes. But averages in space and time are much more stable and change much more slowly. This is both a benefit for us when we try to predict climate change, but it's just often a challenge when we try to apply our knowledge to the problems that people are concerned about in their everyday lives. Additionally, the fact that the atmosphere behaves like a giant resonator and can sustain large-scale waves, the ocean can sustain large-scale traveling waves that can either be stationary or that move very slowly. This provides some predictability as well. So we know that if there's a mass of warm water in the Pacific that is moving towards the Eastern Pacific, that is going to give us an El Nino in a period of weeks to months. We'll see an example of that actually produced by GMAO. a little later in this talk. And that gives us some knowledge of what the climate is going to be on timescales of weeks to months. So how does the energy balance change? Well, greenhouse gases trap energy as it radiates out to space. And this behaves very much in the same manner as when you put a blanket around you and you get warmer. Ice reflects sunlight out to space. But aerosols and clouds, which play a major role in this, are much more complicated. And we have a talk in this panel from Ayantika Choudhury at IITM. IITM is one of the world leaders in dealing with aerosols, having had a long-term observational program and a developing modeling program that's very impressive. So why is global energy balance not enough? And the answer to this can be seen in this picture, which is again actually from Goddard, showing the surface temperatures. And the surface temperature change, Dahlia showed this a little earlier. If you look very closely, you'll see that the surface temperatures do not change by the same amount everywhere. And India is in one of the places where, while there is a temperature change, it is notably less than the polar regions. Right? And so that the mean state change of temperature is something that we have some sense of how it works, although our uncertainties in aerosols and clouds do provide challenges there. But there are also changes across the tropics, and those changes across the tropics drive local redistributions of temperature and precipitation. The plot on the bottom is what my co-chair or fellow organizer Ben Zaitchik says is his favorite picture in the entire climate world. And it shows the changes in precipitation that many of our climate models together predict. And the regions that are stippled are the ones where we have high confidence. And in many parts of the tropics, we actually have relatively low confidence in our ability to predict precipitation. This has to do with the fact that we aren't very good at predicting these gradients from place to place. Dr. Krishnan is going to talk about this more. He's done a lot of really important work on understanding the implications of climate change for monsoons. But another reason that energy balance is not enough is that the feedbacks are not always certain. And this is one of the ways in which the data that places like NASA generate is so important. And finally, observations are incomplete. So I'm going to just talk a little bit about ways in which we can improve our observations. I'm going to focus on some Johns Hopkins and local resources. This part of the US is a hotbed for satellite remote sensing. We have the Goddard Space Flight Institute. We also have the Applied Physics Lab at Johns Hopkins University, which has been building satellites and spacecraft for many decades. An example of a climate relevant satellite that APL has put together is the one that's on the upper right. This CubeSat stands about, I believe the cube is 5 inches on a side or 10 centimeters on a side, roughly. So this is a very small satellite that APL designed, built, and launched to look at the energy balance of the Earth. It uses carbon microtubules to capture radiation. And the thing about these CubeSats is that they're relatively cheap. They can be built for a few $1 million, and they're therefore targets for groups that want to improve our understanding of particular processes, foundations, for example, to actually get in the game. There are CubeSats that have been funded by foundations. Data synthesis is also an area where we have significant expertise. So the plot on the lower right is a very important paper by one of our colleagues at Hopkins, Scott Miller, and it shows how you can synthesize data taken in the atmosphere to monitor greenhouse gas emissions, in this case, methane. The plot on the right shows what the greenhouse gas emissions that go into many policy syntheses showed for emissions in the US. And what Professor Miller and his colleagues have done is to use atmospheric observations and models to say, where are the plumes of actually methane coming from? And one of the things you see is Texas and Oklahoma lighting up, which indicates the impact of gas production and fracking and leaky methane from gas production facilities, right? This was not known before. I think there may be opportunities for us to work with our Indian partners who are making similar measurements to do the same kinds of synthesis work. I also mentioned here that Ben Zaitchik is heading up a new DOE project that will put together one of these networks in the Baltimore area. Again, there may be synergies there, lessons learned that we can transfer back and forth. The other point I want to talk about is how we model this, because we talk about climate models. What do we mean when we have a climate model? So I have a schematic for a global atmospheric climate model on the right here. This involves taking the atmosphere and dividing it up into boxes. You can do this for the atmosphere, you do this for the ocean, you do this for a cryosphere, and then we use the fact that heat, mass, momentum, moisture are all conserved to write down equations that describe how those boxes interact. Some parts of those equations are very well understood. If there is a northward flow in the northern hemisphere, you're going to transport warm air northward. This is relatively simple. Other parts are not so well understood. For example, as we change the stratification, how do clouds change? How does that vary in different parts of the world? How does that interact with aerosols? We'll hear some talks about that in just a minute. Talking about some of our local resources for modeling, a challenge for modeling for a long time has been resolution and how we deal with the large amounts of data. And one place where Johns Hopkins is a leader is in helping to provide open source tools to deal with high resolution models. This shows an example from my colleague Tom Hain, who has a very high resolution model of Iceland, Greenland, and the Norwegian seas, which is a very important part of the climate system, and showing what happens when you put floats into that model and show that the complexity of circulation around a region like Iceland. There are, I think, opportunities. There is now a global version of this model that has been run, and there may be some opportunities to really focus on places like India. One of the challenges in doing climate modeling, and I speak from expertise as someone who spent 15 years at a climate modeling center, is that the models are developed for large-scale purposes, and often, if they do badly in a particular region, unless you look at that particular region, people don't notice. So I think there are some opportunities there. We do have, between Goddard and ourselves, very deep experiences in both building and diagnosing models. And finally, the Global Modeling and Assimilation Office at NASA Goddard develops cutting-edge prediction. And I only recently realized that they're basically using some of the same codes that are run at IITM and ISC. In terms of their ocean models, there are opportunities, clear opportunities for collaboration there as well. So I'm going to finish with a thank you and a dhanyavad and turn that over to my colleague, Dr. Krishnan.
Thank you very much, Dr. Anand. I think you have really set the stage for my presentation. Okay, first of all, many thanks to Johns Hopkins Gupta Klinsky India Institute for this opportunity. And my predecessors really set the stage for my talk. And so climate change is already happening. It's affecting all the parts, all the regions in the world. And there were some very powerful, the planet has warmed by more than 1.1 degrees since the pre-industrial times. So these are some messages from the IPCC AR6 assessment report, which highlights how the human influence has warmed the atmosphere, ocean, and land. And also the changes that we are seeing, they are widespread and rapid. They're happening at a very unprecedented rate. Not just in the atmosphere, but also in the ocean, the cryosphere, and the biosphere, they have occurred. And also there's a very strong regional attribution, and that climate change is already affecting every region on Earth in multiple ways. And the changes that we experience will increase with further warming. So what we are seeing is, this is a quick assessment of the global and regional monsoons. Dr. Anand, are you able to see the slide?
Yep. Looks good.
Yeah. This is again from the water cycle chapter. Shown in this figure are 6 monsoon regions in the world, regional monsoons. We have the South Asian monsoon, the East Asia, the Australia and maritime continent, the West African, the North American monsoon and the South American monsoon. And these dotted areas they're associated with the seasonal movement of the IT season, seasonal movement of the rainfall belts. So the assessment is that the global land monsoon precipitation decreased from 1950s to the 1980s, partly due to anthropogenic aerosols, but has increased since then in response to greenhouse gas forcing and large-scale multi-decadal variability. So the main point is since the mid-20th century, it is not just the greenhouse gases. There have been other drivers like the anthropogenic aerosols, which was highlighted in the previous talks. And in the future, as if we can reduce the aerosol emissions, it's going to be dominated by the greenhouse gas forcing. And so during the 21st century, the global land monsoon precipitation is projected to increase in response to GHG warming in all time horizons and scenarios. This is a high confidence statement. And so in the long term, the global monsoon rainfall, which is basically shown by this black line, it will feature a robust north-south asymmetry characterized by greater increase in the northern hemisphere than in the southern hemisphere, and then east-west asymmetry characterized by enhanced Asian African monsoon rainfall. So that's an important message. The Asian and African monsoons are projected to increase in the 21st century. But increases can happen not just in the mean, but also due to the increase in the extreme precipitation. So I will just take you through these slides on the Indian summer monsoon. It's really a complex dynamical system which involves multiple scales, interactive scales. And this picture again is from one of the NASA schematics which I had borrowed. It has been slightly tilted. The directions are shown north, south, east, west direction. You have the Tibetan Plateau, the Indian landmass, the Indian Ocean. And basically the thermal contrast between the land and ocean sets up the monsoon circulation. And when the winds, they blow from the Indian Ocean towards, it crosses the equator, you have the winds picking up moisture from the Arabian Sea. And during this time, it also interacts with the African coast. You have the East African highland mountains. And so when the winds interact with the ocean, they also drive strong upwelling in these areas. And you can see the increase in the chlorophyll concentration from the ocean. You can see this from the satellites. This is from the CWIPS data. So basically, and then this cold water brings the nutrients, it brings the primary productivity, it cools the ocean. And then there's a lot of evaporation, the water vapor, due to the evaporation, the water vapor fluxes, it takes the moisture. And when it interacts with you have the orography, the Western Ghat mountains and the Burmese mountains on the further eastward, you have the formation of the cumulus clouds, which organize on very large scale. And they are going to sustain the monsoon. They keep producing rainfall. But as the water vapor condenses and forms clouds, it's also going to release huge amount of latent heating. And now the satellites, the TRIM satellite and the GPM, they're able to estimate how much is the latent heating from these convective systems. So this is truly a complex dynamical system where the atmosphere, land, ocean, and the biosphere, they are interacting with one another. And year-to-year variations in the monsoon rainfall, they can be affected by internal variability within the region and also by remote drivers like the El Nino Southern Oscillation, which I'll be showing in my next slide. And now there is climate change on top of that. So there are multiple scales involved. So this is a big plot of the rainfall, the climatological rainfall over the Indian landmass. You can see the rainfall is not uniform. It's more over the Western Ghats, where we have the orographic precipitation, and also over Northeast India and the eastern part of India, and substantial amount of rainfall over the what we call as Central India, the core monsoon zone. And this is the time series of the interannual variability from 1871 to 2021. We see a significant interannual variations and also decadal variations. And many of the deficit monsoon years are during El Ninos, all these red bars. And the blue bars are the years when there was a La Nina event in the Pacific. So normally during La Nina event, we tend to get excess monsoon. And but there are also many years that are not associated with ENSO. Monsoonal variations are not really associated with ENSO. Overall, when we look at this long-term monsoon rainfall time series, we see that second half of this period was marked by more number of droughts during this period, and there has been a slight recovery in the monsoon rainfall in the recent few years. And in fact, the extreme precipitation has been increasing. Precipitation more than 10 centimeters per day or 15 centimeters per day. Those events are occurring more frequently. One of the consequences of climate change is the increase in the water vapor or the water vapor feedback because of the temperature dependence on the saturation vapor pressure. So due to this, for every 1 degree rise in the temperature, the water vapor in the atmosphere is going to increase by something like 7%. And one of the direct consequences of this increase in the water vapor is the increase in the frequency and intensity of extreme precipitation events, which is also observed in many places around the world, including the Indian region. And more recently, we had the Pakistan floods in July, and it was very, very extreme. And so this was I just took this paper from the Views, Nature Views by Smriti Mallapati. So this was 1/3 of the country is underwater, and it was just before the heavy precipitation. It was followed, it was preceded by intense heat waves, and immediately thereafter, in early June, the monsoon had set in. And many places during the pre-monsoon months, during the April and May, they had recorded very high temperatures. One place called Yaqubabad topped almost 51 degrees. And these are not normal heat waves. And so this was a kind of trigger. The land was already getting warm. And then the monsoon also arrived a little bit early in this part of the world. And there was, in fact, a large-scale depression that ensued. And that was one of the triggering points. But incidentally, due to the strong warming in the pre-monsoon month, there was also glacier melt in the Himalayan glaciers, which also added to the runoff. So when the flooding happened, it was not just the rainfall, it was also associated with the glacier melt. And more importantly, there were other large-scale dynamical features, like there was an ongoing La Nina. In fact, this La Nina has been continuing right from 2020, and this year, 2022, was particularly very, very strong. And I'll show you some of so this La Nina type of situation, very intense La Nina, can have profound implications on the Indian region and the monsoon precipitation over South Asia. These are again some pictures that I picked from the GPM IMERG satellite product, again a NASA product. And this is I have the information for June, July, August of 2022, and superposed on this rainfall are the winds from the European reanalysis. And this box is the region where I'm showing over Pakistan and Northwest India. And we also see a very strong La Nina during this June and July months. This is a sea surface temperature anomaly. You can see the Western Pacific, you have a very large cooling in the Central and Eastern Pacific, whereas the West Pacific, the tropical West Pacific, is anomalously warm. The ocean heat content is very high. Also, the Eastern Indian Ocean, equatorial Eastern Indian Ocean, and the Bay of Bengal are relatively substantially warmer. And this is the time when the convection kind of increases in this region. And due to this very intensified La Nina, because of the stronger enhanced subsidence further in the subtropics, the West Pacific subtropical high was very much intensified, and it had extended far to the west. And this is the vertically integrated moisture transport and the flux of water vapor. You can see that the water vapor is being transported from the Bay of Bengal and also from the Arabian Sea very much into this region where the land was heated up, the area over Pakistan. And this picture shows the daily rainfall averaged over this region, over Northwest India and Pakistan from GPM and IMERG. So the rains that we see during June and July were substantially much higher than the climatological mean. And also these spells were long lasting. And so the main point is this precipitation is driven not only by this increase of the global mean temperatures and increased evaporation, also these climatic variations like a very strong La Nina conditions, they can affect the large scale patterns rearrange the moisture transport, and they can trigger heavy precipitation events. And in fact, when I look at the difference between the JJA 2022 minus 2021, you can see very strong flow of winds and the moisture from the eastern, from the Bay of Bengal, South China Sea. It's all directed towards the Pakistan region and also from the Arabian Sea. So it's really a large-scale phenomena that is contributing. And the interesting point is, during May and June, the land was very, very warm, and there was subsiding motions. It was very dry. There was subsiding motion. This is at the 500 millibar winds. The land was basically getting heated up. And this was a picture by paper by Bob House, who is an expert on these cloud systems. So one of the mechanisms for this intense precipitation, heavy precipitation in the area of Pakistan is because when the land gets heated up, the Afghan plateau, and you have dry subsidence happening, and at the same time you have the ocean, you have the moist winds coming from the ocean. There is a surface heating. So when this moist wind comes into the desert region, and you have the dry winds from the north, this can really increase the convective instability in the atmosphere. Can develop, can intensify, and then the deep convection happens. And in fact, we are seeing this signature very clearly during 2022. And the main point is that this also happened during 2010. So the Pakistan region also experienced floods during heavy rainfall and floods in the upper Indus Basin during 2010. But 2022 has been much more severe. And we see very similar signatures of a very strong La Nina in 2010. And this was based on our climate model experiments, how the La Nina conditions, this from the observations and this is from the model. So these large scale drivers can actually alter the circulations and direct the moisture flow and be an important triggering mechanism for this heavy rainfall over this region. And the main point is that, so with climate change, as the water vapor is going to increase in the atmosphere, the transport of water vapor is going to increase and the convergence is going to increase, which is what I highlighted. And this is going to be a very important problem. And especially in the tropical areas, heavy precipitation and the moisture transport is going to be a key issue. And so satellites will have a very, very vital role in predicting these extreme events. And we also need to improve the models to capture these organized convection and these moist processes and heavy precipitation. And the IITM is involved both in observational studies and also climate modeling studies. In fact, the first climate model from India, the Earth System model from IITM, participated in the recent IPCC, AR6 assessment and also the CMIP6 projections. But we still have to go a long way because there are many uncertainties when we talk about regional monsoons. So the models have to be improved. So NASA data sets are going to be very, very important for this, for improving the models and also for developing adaptation strategies. Thank you very much. With this, I will end my talk.
Great, and I'd like to introduce our next speaker, Dr. Ayantika Choudhury. Is a researcher at IITM, and she has worked extensively in aerosols and climate modeling, and she's going to talk to us, follow up on this talk about and bring together some of the work on aerosols and clouds and the monsoon.
Thank you, Professor Anand. So I'll just share my screen. Okay, so today I will be talking on aerosols and how it impacts climate, mostly focusing on how it impacts the precipitation. As we know, aerosols are a major anthropogenic short-lived climate forcer. It is emitted through anthropogenic sources as well as natural sources and acts as air pollutants, but it also changes the energy of the system. So it changes the incoming solar radiation by absorption or scattering. So it reflects much of the solar radiation back to space, giving rise to albedo changes. And through these radiative changes, it changes the temperature, it impacts precipitation, weather patterns, as well as it impacts the cryosphere. So we know that during the historical period, especially from 1950s, there has been an increase in aerosol emissions over various regions in the globe. So this is the global mean aerosol optical depth from CMIP 6 models. So this black line is the multi-model mean. So we can see from 1950s onwards, there is a steep rise in the aerosol optical depth of 500 nanometer, which is representative of the aerosol loading. And it stabilizes around after 1990s. And this is due to reduced emission over some regions like Europe, North America, whereas increased emissions over other regions. Now, if we look into the radiative changes of these aerosols, we find that these aerosols deplete the radiation, solar radiation, and produce a negative radiative forcing. So it reduces the energy in the climatic system. And this negative energy deficit is more prominent over regions where the aerosol loading is high, mostly the continental regions, especially India, East Asia, Europe, and North America. Now, if we looking into the fingerprint of temperature and precipitation, so we see that the first leading fingerprint is from the greenhouse gases, which is shown here in the left-hand panel, and it shows a universal warming. But when we look into the fingerprint of aerosols, we find that there is a hemispheric asymmetry. So there is cooling in the northern hemisphere. So the aerosol forcing, it produces cooling over the northern hemisphere, mostly the continental region, whereas it produces warming over the southern hemisphere. So there is a strong gradient, north-south gradient in temperature. And the precipitation fingerprint of aerosols, it shows a large-scale reduction in precipitation, mostly over equatorial region and tropical region. So it impacts the monsoonal systems. Now, the difference between the greenhouse gas and aerosols are greenhouse gas are very homogeneously distributed, whereas aerosols have a heterogeneous distribution, as well as they have a very short lifetime. So basically, they are more confined towards the source regions and towards where it gets transported. So we have high aerosol loading, mostly over India, China. Then we have East Asia, which is transported across the Pacific. We also have the European plume and the African region from biogenic sources. We have aerosol plumes, the Amazonian plume over South America. So this non-uniform distribution of aerosol loading, it creates an uneven heating distribution in the atmosphere and a cooling at the surface because it depletes the surface radiation. So it produces cooling at the surface, as well as the absorbing aerosols. They absorb the incoming solar radiation, so they heat up the atmosphere. Now, these non-uniform heating and cooling patterns, they drive changes in atmospheric circulation and the regional rainfall. So they impact the precipitation. So we have seen that the anthropogenic aerosols have produced changes in the hydrological cycle through their radiative effects. So here we have we show the northern hemispheric. We see the northern hemispheric shortwave radiation anomalies, global mean. So the black curve here shows the change in the radiation anomalies from 1960 to present day. And the red and blue curves here shows the changes due to aerosol forcing and the all forcing. So we can see a decrease in radiation anomalies in similar to the increase in aerosol concentrations. So we see that it's consistently decreasing from 1960s till 1991, which we know as solar dimming. And then thereon, there is a slight increase. Now, if we look into the summer hemispheric precipitation anomalies, mostly the precipitation anomalies have been averaged over the monsoonal regions like South Asia, East Asia, Africa, West Africa, and South America. And we can see that this is the observed, the black lines are the observed change in the precipitation. So we see it follows the declining curve of the radiation anomaly. So there is a decline till around 1990s. Then there is a recovery in the precipitation. And in the aerosol forcing, which is shown by the blue line, we also see a decrease in precipitation from the semiparams, whereas there is an increase in the GAG forcing. So the decrease in precipitation is mostly contributed by the aerosol forcing. So focusing more on the South Asian region. So this is the trend and precipitation change over South Asia. Now, the dots here shows from the observations, the trend in the observations, and the box plots are trends from the models for different experiments. Like the black one is when we have all forcings, like all anthropogenic natural forcings included in the model. The red is when we have only the GAG forcing. The green here shows only for the aerosol forcing, and the blue is for the natural forcing. So we see that for the South Asian region, over the past 50 years, from 1950 to 2014, there is a declining trend in precipitation. And the models capture, the aerosol forcing in the model capture a very large negative declining trend. So aerosols produce a declining trend in the monsoon precipitation, whereas we see that the greenhouse gas forcing, which is the red here, it shows a positive trend in precipitation. But the combined all forcing experiments, like when we have GAG, aerosols, land use, land cover changes, as well as natural forcing, it shows a reduced precipitation change. So this basically reflects the reduction in the aerosol forcing. So taking a closer look on this, how the South Asian monsoon system responds to aerosol and greenhouse gas forcing, we have conducted some sensitivity experiments using IATM ESM. So here is the anthropogenic aerosol, the JJ is summertime anthropogenic aerosols over the globe. And we have different plumes which correspond to the emission sources over different regions. And using this anthropogenic aerosols, we have done some experiments. Like for a pre-industrial state experiment, we have kept the aerosols at pre-industrial level, as well as carbon dioxide at the pre-industrial level. For the aerosol experiment, we have put this anthropogenic aerosol forcing into the model and kept the carbon dioxide into the at the pre-industrial level. Then for the greenhouse gas forcing, we have kept the aerosol at the natural pre-industrial level, whereas we have changed the carbon dioxide forcing and we have increased the carbon dioxide values to present day level. Then finally, we have a combined experiment. We have the present day aerosols as well as present day carbon dioxide. So when we analyze the changes in monsoon circulation and precipitation, we find that when we put the aerosol forcing, the anthropogenic aerosol forcing in the model, there is a large scale reduction in precipitation. This is the JJA's precipitation. So there is a large scale reduction in precipitation extending from Arabian Sea across till South Asia. But for the greenhouse gas experiment, we find the greenhouse gas forcing, it produces an increase in precipitation. But interestingly, when we look into the combined forcing, we see that the aerosol forcing counteracts the increasing precipitation in greenhouse gas forcing. And we see for the combined, when we have both the forcings, we see a extended reduction of precipitation over extending across Arabian Sea till Southeast Asia. So we can say that this effect of aerosol, it counteracts the effect of increasing precipitation effect of greenhouse gases. So what happens is basically when we analyze the radiative forcing, we find that there is a large deficit, very strong deficit of radiation over the South Asian and East Asian region due to the high aerosol loading. Now, this deficit of energy at the surface and at the top of the atmosphere, it creates a north-south energy deficit, energy gradient. So if we average this radiative forcing, we find that this blue line is the greenhouse gas forcing. So we find across the latitude, it is quite uniform. But for the aerosol and GAG, which is shown by the green and, by the red and the blue, black curve, we find that there is a very strong north-south gradient. So we have in the surface, we have a gradient which is almost 15 watts per meter square. So this strong, very strong north-south gradient in energy, it changes the circulation. So here is the lower level circulation and evaporation. So we see that there is a large anomalous anticyclone. So the winds have slowed down over the South Asian region. This is very prominent in the combined experiment. So this is the combined experiment. So we can see that winds are diverging from the, instead of converging, this is the anomalous winds. So they are diverging from the subcontinent towards the equatorial Indian Ocean. And the shading here, it shows the evaporation. So with the slowing down of circulation and the reduced temperatures, there is a large-scale reduction of evaporation. So the moisture has reduced, the winds are slowing. So there is a divergence. So the anomalous moisture divergence occurs over this region, which basically weakens the hydrological cycle over this region during the monsoon. And it is done through the help of the aerosol forcing. So, and this weakened circulation, it reduces the organized precipitation. As we know, there are very deep clouds, which we saw just now. So it extends across this entire subcontinent towards Southeast Asia. So this organized convection gets weakened. So the vertical velocities are representative of organized convection. So we can see this red here means the vertical velocities have decreased. So for the combined forcing experiment, where we have aerosols as well as greenhouse gases, so we find that the organized convection decreases and it reduces the clouds and it reduces the precipitation over this region. Now, the effect of aerosols has been also observed in other monsoonal regions like the West African monsoon. So this is the precipitation change over the West African monsoonal region from 50s to present day. So we see from 1960 to about 1990s, there is a decrease in observed precipitation, and thereon there is a recovery. And this middle plot here shows the radiative forcing due to aerosols. This green and blue and the violet plot shows the radiative forcing over Europe, Africa, and North America. So it shows a decrease in radiative forcing. Now this increased radiative forcing, the enhanced negative radiative forcing, it creates a interhemispheric pattern of SST anomalies, which influences the West African monsoon. But thereon, with the reduction of emissions over North America and Europe, and also with the increasing greenhouse gas concentrations, the combined effect of aerosols and GHGs, this led to a revival of the monsoonal precipitation over West Africa. Now, along with the radiative effects, aerosols also impact precipitation through its cloud microphysical processes. So, for example, if you have a clean environment and then we introduce absorbing aerosols in the planetary boundary layer, it changes the temperature profile. So here we have this dotted line is the temperature profile for when we don't have the absorbing aerosols, and the solid line is the temperature profile when we have aerosols in the planetary boundary layer. So we can see that with the introduction of aerosols, it absorbing aerosols, so it absorbs the incoming solar radiation. Therefore, it depletes the radiation at the surface, which leads to surface cooling, and it leads to a negative energy in the lower levels, which raises the cloud condensation level, and hence it suppresses light rainfall. Also, more number of aerosol particles. It means that it would create smaller droplets, and which will not coalesce to grow into bigger clouds. So therefore, it will suppress shallow convection. But on the other hand, when we have deep clouds, this temperature profile gets changed such that there is positive energy in the upper levels. So when we have very high updrafts, and which frequently occur in deeper clouds, and the water vapor particles are carried upward, then we can expect heavier rainfall from deeper clouds. So this is a competing effects, and it depends on the concentrations of aerosols, the cloud condensation nuclei, and how the aerosol interacts with the ice nuclei or the water droplets. And this is a very open area of research, which is still a lot of work is going on. So I'd like to summarize by saying that aerosols have an impact on the regional climate variability. Aerosols have caused detectable changes in the hydrological cycle since the mid-20th century over South Asia. It has been shown that aerosols resulted in a decrease in monsoon precipitation, the significant energy deficit that occurs at the surface over the aerosol-dominated regions. It weakens monsoon flow, and it offsets or overcomes the expected precipitation increase that happens due to increased GHGs. But there are a lot of challenges still in understanding how aerosols interact with climate, basically through the cloud aerosol interactions. These effects are muted in GCM. So, and also we have limited understanding like how deep clouds, the aerosol processes in deep clouds occur, like the ice nucleation, which we can see in the deep clouds. And the parameterization schemes in the GCMs, they are still not able to simulate these aerosol-related perturbations in the cloud droplet concentrations and ice crystals. So I would like to end by saying that there is need for an improved representation of deep convective clouds and their interactions with aerosols for improvements in the GCM simulated precipitation. Thank you.
Great, thank you. We have, I'd like to again invite people to type questions into the Q&A. And we have some time for questions and discussions. So Dr. Krishnan, we have a question about the retention of water vapor in the upper atmosphere leading to extreme rains. Does such retention also capture air pollutants in the upper atmosphere leading to poor air quality in such areas before the air quality getting better due to subsequent rains?
I just responded to this question by Dr. Pradeep. So when extreme rains happen, the convection basically carries the water vapor from the surface upwards into the middle and upper troposphere. And sometimes small amounts of water vapor can also enter into the lower stratosphere. And now there are some studies, they suggest that during the Asian monsoon region, the monsoon convection can transport air pollutants and trace gases into the upper troposphere. And this is known as a ATAL, the aerosol layer in the Asian monsoon aerosol layer in the upper atmosphere. And this is not fully understood. Some studies argue that these pollutants in the upper troposphere may be transported from remote locations. But there's also a school of thought that believes that it is carried from the surface to the upper layers. So this is a topic that is being researched using satellites. Satellite, they provide information about these aerosols, the ATAL layer in the upper troposphere. And there's also this monsoon anticyclone in the upper troposphere. So when the convection develops in the upper level, we have a very large scale anticyclone known as the Asian monsoon anticyclone. And they continuously take the water vapor and the pollutants around the anticyclone in the upper troposphere. So the question about pollution, whether it is coming locally or whether it is being transported, there's a long range transport. I think that's a topic of research, ongoing research.
I would also add that Dr. Choudhury's second to last plot, where she was showing the differences between deep convection and shallow convection, is also relevant to this air pollution, climate change question. We have published work showing that you can have regions where the total precipitation goes up, but the air pollution also goes up if you shift your precipitation from drizzle to deep convection, because deep convection is more intermittent and drizzle is actually much more effective at scrubbing the atmosphere.
Okay.
So we have a question here. Thank you for such an informative session. What is happening at the policy level to mitigate future climate catastrophes? What actions are being taken? Are there any outcomes that can help us understand that progress is being made to mitigate climate change related challenges? We had a similar question about that ended up in the chat earlier. And so I'm just going to answer them together. Basically, there's three ways in which we're thinking about this right now. One is that we can reduce emissions. The second is that we can sequester carbon. And the third is through actual geoengineering activities. In terms of emissions reduction, I think it's not widely appreciated that significant progress has been made in reducing the carbon intensity of economies around the world. In the US, it's like 60%. Lots more needs to be done, but I think it's important to realize that we are actually making significant progress. This is also going to be the case if you think about not just carbon intensity, but the intensity of other air pollutants. actions like the Clean Air Act in the US have saved literally millions of premature deaths. So we know how to do this. In terms of sequestration, there is a carbon offset model that is built around human activities to sequester carbon, and the most recent Inflation Reduction Act actually provides lots of money for technology demonstration projects of that as well. Again, not enough is being done, but stuff is being done, and more is being done than people realize. Now, geoengineering is definitely in the research stage, and part of it is for some of the same reasons that my co-panelists have talked about. We understand many of the effects of greenhouse gases and aerosols on climate change, but the regional effects can sometimes add up in unexpected ways. Like Dr. Choudhury showed, that generally greenhouse gases and aerosols counteract each other, but there are regions around India where they add up, right? So understanding that is one of the challenges with geoengineering, and figuring out how you generate a global governance system that can deal with that is another challenge. I'll turn that over to my co-panelists if they want to add anything.
Yeah, thank you, Dr. Anand. I just want to add to what you said. Dr. Ayantika also showed in her presentation, the West African monsoon has been recovering since the 90s. This is partly due to the regulation in the aerosol emission norms in North America and Europe, together with the increasing GHG forcing the greenhouse gas concentrations. They have increased, and also the aerosol regulation norms, because of the improved regulation norms, the precipitation over the West African monsoon has slightly recovered. This is what is the assessment in the R6. So one possibility is that the decarbonization can happen in the long term. That's a long-term process. It's going to take time. In the short term, reducing this air pollution is also going to provide benefits. So I think this combined strategy will be important, at least for the recovery of the monsoon precipitation. This is going to be important. We need to have a strategy for that.
I actually have a question for my co-panelists. In terms of geoengineering, what's the state of discussion right now within India in talking about geoengineering and cloud seeding and climate modification?
Yeah, there is some work going on geoengineering, not many studies. But for cloud seeding, IITM has done some experiment. It is known as the cloud aerosol interaction for precipitation enhancement. And this started sometime in 2009. And we had 3 or 4 phases of, this is known as CAPEX, 4 phases of CAPEX, where they had aircraft experiments, nearly 1,000 hours, more than 1,000 hours of flying. They had a seeder aircraft, and then that was followed by another aircraft that used to. Then they did some randomized cloud seeding analysis to determine what is the efficacy of cloud seeding for the precipitation enhancement. And apparently a report has been submitted to the ministry. If we do cloud seeding, what happens? And that has to be publicly, they've done a good job. A lot of good scientific work came out, but it's also policy relevant. So the report has been submitted. I think the results are indicating that there is a 30–40% chance of precipitation enhancement. Probably some more samples will be needed, because if you want to really do this assessment, you need large number of samples to do the statistical analysis. But it's looking promising. There is a potential, maybe about 20–30% feasibility for enhancement. But clouds itself, they're so stochastic in nature, and so the variability is going to be very complex. That's what is the issue.
So there was also a follow-up question about air pollution and precipitation interactions in the upper troposphere, about the data to analyze that being publicly available. Is there the equivalent of the,
Yeah, I think the data is, so probably all the data may not be available, but maybe I can talk to my colleagues and we can make sure that the data is, if people are interested to do the research, it can be shared. I think it should be possible.
So I thought it might be helpful. One of the charges that we were given in this panel was to talk about potential collaborations. And I thought it might be helpful if my fellow panelists talked about some of the things that they would be interested in seeing from a collaboration here. What are, in terms of having people maybe visit there, people visit here, what are some of the topics that we might be interested in?
Yeah. So one of the, I think the climate modeling area, there's a lot of opportunities because cloud aerosol interactions in the monsoon environment, there a lot of observations are there, how to put them in the model. I think that is something that is we don't understand. Here we have a lot of warm rain processes. These are not really the deep convective clouds with, yeah. So the monsoon rains are more of stratiform rains. They're tall clouds, and the cloud microphysics is not really well understood. Especially in the Western Ghats, the clouds are not very deep, but they can give a substantial amount of rain. So these are how, so the question is how the clouds and aerosols, how they're interacting to produce these raindrops. I think that's very important now, and how they can be represented in the models. So there is an opportunity there. And also, for example, the monsoon, one of the problems, all the CMIP 5 models are CMIP 6 now. This problem of monsoon precipitation, this legacy has continued from CMIP 3, CMIP 4, CMIP 5, CMIP 6. There is a dry bias. Now, to some extent, it has been reduced. This problem is because it may not be just a local problem. Because once if you have a bias in the precipitation, that means your latent heating is going to be underestimated in the model. And if the latent heating is underestimated, the winds are going to be weak. And if the wind is going to weaken, then it is going to affect the sea surface temperature. And this, it's a kind of vicious cycle, one affecting the other. And these biases are going to propagate in the Earth system models. And we need a good way. How do we reduce this bias? I think that's one of the important problems. How do we do that? So now there's a lot of data, whether we can use data-driven techniques, use machine learning, because with so much of satellite data, can we improve some of the model physical processes, how to represent them in the models?
Right,
so those are, yeah.
And as you say, I think one of the challenges is that those processes may not just be in the atmosphere; they might be in the ocean, for example. Right, absolutely. Because you outlined a positive feedback loop, and you can trigger that feedback loop at any point. Right.
Absolutely.
That, yeah, I hope gives those of you who don't spend all your time thinking about climate a flavor of some of the kinds of things that we think about. Dr. Ayantika, do you have any thoughts on this?
Yeah, like I would like to add that the vertical profile of heating is very important to correct the circulation. And with the help of this GPM, TRMM, there's a lot of data. We have the data on the cloud processes, how the clouds develop in the vertical. So that information, if we can put in the global climate models, that will be very useful for improving the circulation.
Right. I think that there's some opportunities for you learn a lot by comparing models too, because one of the problems that we have in our community is that when models are developed, the development cycle is so intense that people are trying lots and lots of different things, and of the things that get tried, maybe a quarter of them actually get published. And so there's lots of knowledge in the, you see you laughing too, right? So there's lots of knowledge that sits in the brains of individual people in the modeling centers like GMAO and GFDL and IITM that never actually gets exchanged. About, did you see this phenomenon? Oh, yes, we saw that too. Maybe we should write a paper together. And so I think just making sure that we have more opportunities to exchange that knowledge is really important.
Yeah, and also maybe the land and atmosphere interactions. Those are not well understood or well represented in models. A typical example, as I was showing this Pakistan heavy flood, was preceded by intense heat waves. So the question is, how good are these models in getting those type of interactions. And then suddenly you transition from the pre-monsoon to a very, very intense wet monsoon. And that's where the land surface process, the soil moisture feedbacks, so the exchange of fluxes from the surface into the atmosphere. I think those are going to be very important processes.
Great. Well, we have a couple of questions in the Q&A that I will get to. We have to move on to the next panel, and I want to thank my co-panelists for a really informative discussion here.